Okay, again, thanks everyone for sticking around. I want to introduce to you and also, I guess, introduce for myself for the first time, get to be introduced to. Dr. Don Woodard is a Senior Director of Data Science for Platform Technologies at Uber. These include Uber's experimental platforms and mapping and location systems, such as map search, route optimization, travel time prediction, and navigation. Dr. Woodard received her PhD in statistics from Duke University, so a neighbor of mine here in North Carolina, after which she joined the faculty of the School of Operations Research and Information Engineering at Cornell. Her research focused on prediction and machine learning for vehicle fleets and bike sharing, helping to lay the groundwork for the burgeoning rideshare economy. After receiving tenure at Cornell, she joined Microsoft Research for a sabbatical, where she created travel time prediction methods for use in Bing Maps. She then transitioned to a role at Uber, building and leading the marketplace technologies such as dispatch, pricing, and incentives before transitioning to her current role. So with that, welcoming to the ISF for, I believe, the first time.
Yes, that's right.
Dr. Don Woodard. Don, take over.
Thank you so much, Mike. We're delighted to be here. I'm really excited to talk to you today about some of the technologies that we develop in the context of ride-hailing platforms like Uber. Of course, you might be familiar with some of our competitors as well around the world. And I lead the platform technologies. That includes all of our geospatial or mapping technologies that I'll talk about in a moment, as well as experiment platforms, financial technologies, machine learning platforms, and more. So our mapping team in particular creates all of these technologies that are needed across our different lines of business. That includes the rides business, when you request a ride from point A to point B. Our Uber Eats business obviously has become much, much more important during the pandemic globally. And we also have a business in freight, peer-to-peer platform as well. All of these systems leverage these basic underlying technologies for things like location estimation. So how do we estimate where a user is at a given time? That's a couple of different mathematical problems, including estimating location based on multiple location signals, GPS, sensor data like inertial measurement unit or Wi-Fi. So combining that different information to estimate a user's location at a given time when they're engaging with the app. Or you can think about, for a driver, for example, we know that that driver's on the road network. So estimating that location on the road network, given the GPS points, that can be quite challenging in downtown areas, for example, where GPS signals can get reflected off of tall buildings, and there can be quite a bit of uncertainty or displacement of that GPS signal. So once we have that estimated location for a user, there are a set of technologies for our users to interact with directly with our systems. For example, you as a rider may go into the app and specify a destination where you'd like to go. And often you're doing that using either our destination predictions. So we give you a couple of options of places we think you might be going based on your past history, or you might search for that destination using our GeoSearch technology. So entering the name of a hotel, for example, or an address that you're going to. So we need to be able to recognize what you're typing, and then of course provide a set of geographic search results in the app. Also used in our Uber Eats service, for example, when you're specifying the drop-off point for your food. Some of the other foundational mapping technologies that we develop in-house include route optimization. So this is when you are in the rider app, you can see the route that a driver is going to take to pick you up. On the driver's side, we provide turn-by-turn navigation for drivers, and I'm showing that in the top right. We're navigating a driver to drop off food at an apartment complex. So what is that route objective function? Do we think about minimizing time? How do we take into account distance in that objective? The things like the road classification. So people generally prefer highways over alleyways, for example, if the travel time is the same between those two, how do we take into account things like left-hand turns, which can be slower and more dangerous than other kinds of turns? A lot of different factors that go into something like route optimization. The technology that I'll talk about today is called travel time prediction. It's also known as ETA prediction, and that's whenever we predict time from point A to point B for a bike courier or for a driver who's going to drive a passenger. So what's that time to destination? What's that time to pick up? These things are used throughout our services. And for things like dispatch, we have to know the time from point A to point B in the road map, which is the relevant sense of proximity in Uber's world. So everything's created on the basis of a map. And because this is a logistics platform, everything involves map technologies. In particular, I'll talk today about the technical problem of travel time prediction. So once we have a route, and here I'm showing a navigation service where we may be showing multiple routes, focusing on one of those routes. If we know when the driver is going to start driving along that route, we need to predict the time to destination. So again, predicting total travel time. And I'll focus on the case of a driver today. In general, it could be different kinds of modalities, from walking to biking to driving motorcycles, etc. This again is used throughout our app. And here's an example where in the rider app, we show the predicted time to pick up. Here it's 2 minutes. And we also show the predicted time to destination, 9:43. Again, use several of these travel time predictions. And in fact, in every one of Uber's rides trips, on average, there are thousands of calls to Uber's ETA prediction engine. Particularly in services like Uber Pool, where we have to calculate many, many possible combinations, you can see that the number of queries to this service could be quite large. The number of different possibilities for matching riders to drivers, or for matching Uber pools together and meeting travel times between all the different waypoints in that potential match. Here's another example. The travel time predictions are used when we calculate the prices. And so in this example, in many regions, we provide an upfront fare to our riders in the request screen. And so here you can see prices for different ride options. That price is based on the predicted time and predicted distance on the route shown in the app. And that's because on the driver's side, drivers receive payment according to the time and the distance to destination. And so at the time at which the rider requests, we don't know precisely what that time and distance is going to be. So we have to use a predicted time, predicted distance. If we overpredict, then that rider's less likely to request. If we underpredict, then the platform will lose money, right? So the accuracy of these predictions is very, very important for some of our pricing applications. I mentioned the navigation use case, and this is very directly user-facing. Again, we show multiple routes in the app associated with the predicted times for those routes, and give drivers some options about how they want to get from point A to point B. Again, our matching or dispatch engines, particularly in cases like high-capacity vehicles, Uber Bus, which we have live in several cities in the world during this pandemic recovery, and also Uber Pool, which has been offline for some time around the world, but it will gradually come back during recovery. But even in UberX, where it's just matching one driver to one rider, there's a step in which the drivers are being matched to riders who are requesting rides in a batch step. And during that matching step, we need to know, again, predictions of time for any potential driver to pick up any potential rider. And so how do we think about this problem? What's hard about this problem as a prediction or forecasting problem? You might think, okay, there's so much data and historical data about the travel times in the road network from Uber drivers who are on the platform right now or have been on the platform in the past. And you'd be right, overall, the total volume of data can be quite large, but there actually still is a data sparsity issue, because what we're trying to do is predict for any given route or any given road segment in the network, what is the predicted travel time for that part of the road network? And so for many routes, there may actually be no historical data that took that route specifically, or even for individual road segments in more rural areas, for example, we may not actually have historical data for that road segment or that route specifically. And so there is actually still a data sparsity issue that I'll dive into. The speed depends in a complex way on the time of week, the location, is it an event or a holiday, the road classification, highway, arterial road, number of lanes, etc. And so the types of data sources we use, first, the road network information itself. So this, again, where are the road segments? How many lanes do they have? And how does the lanes in one road segment connect to the lanes in the next road segment, which is important for our navigation functionality. All those road segment features, the information about number of lanes, the road classification, the speed limit, etc. Again, these are all features that can go into a potential machine learning model. And so as you think about the core data that's used for predicting travel time in the road network, it's quite natural to look at historical trips and the sequence of location estimates for the driver during that trip. And here I'm showing a particular trip in downtown San Francisco, and I'm showing the location estimates at each point in time. And you can see that there's a bit of noise in the raw location estimates during the trip. So in order to use this data, we actually have to pre-process it to match it to the road network and to estimate both precisely what route was taken and the amount of time spent on each road segment in that route. And I'm illustrating this for this trip. We can estimate that perhaps 30 seconds was spent on the first road segment and 20 seconds on the second road segment, etc. And so that process data can be used to obtain average travel speeds in real time or based on time of week, for example. And here I'm showing it in the downtown San Francisco area, where the color is based on the estimated speed at this time, which is an evening rush hour, relative to free flow or maximum speed. And so the red is showing a congested roadway and the green is showing an uncongested roadway. And you can see the richness of the real-time information that can be available particularly for some of these heavily trafficked road segments. And so again, we have to take into account some complex effects associated with things like time of week. And so here I'm showing the average speed on highways in downtown San Francisco by time of week. You can see this is pre-COVID data. You can see very dramatic effects associated with morning rush hour and evening rush hour. Fridays actually have different patterns from Mondays through Thursdays, etc. Have to take into account this type of data effectively. And so what's the simplest thing you can do in order to obtain travel time estimates? Probably the most common method for this is to fit a machine learning model to the individual road segment travel times. And so you're predicting, say, the 30 seconds in this illustration, that travel time on an individual road segment, which is the section of road between two intersections, using the features that I've mentioned so far, or in addition to things like estimated real-time traffic speed based on the data that's coming in right now, for example, and some of those signals like the road classification and time of week that I mentioned. So you can fit this machine learning model at the road segment level, and then you could most simply think about, okay, I need to just add up or aggregate in some more sophisticated way across the segments of the route. And one thing I won't talk about is how to take into account intersection effects, but just trust me that we can kind of bundle this into this kind of prediction approach. And so that's a very straightforward way to obtain a travel time prediction from point A to point B, and probably one of the most common ways. It's very computationally scalable because there are hundreds of thousands of road segments in every metropolitan region. And so this is something that can be easily done at the level of those individual road segments, and then aggregated up in real time for any specific route that we're interested in. This approach captures these really rich physical dynamics associated with the road network. Things like there are traffic lights that can cause particular traffic effects on individual road segments. And if we're fitting models at the road segment level, we can start to capture some of this complex dynamics by time of week interacting with traffic signal effects, for example. So you can capture that richness that we know that exists in this traffic data. On the downside, because you're fitting at the level of the individual road segment and then aggregating in some way, the errors do accumulate across the road segments, and there's a kind of discrepancy between the granularity at which we're doing estimation and then the granularity at which we're doing prediction, which is this route level prediction. And so that can introduce some noise, if you don't do it carefully, it can introduce some bias in the process because it's this multi-stage approach. And just to illustrate that challenge, here's the separate road segments for a particular part of the road network, and highways in particular, you can see can be quite chopped into short road segments. And so again, there is this discrepancy between this modeling at the small level of individual road segments and then adding those up, we're actually trying to predict at the level of the whole route. And so some people actually do this in a completely different way. And this techniques were inspired by trip data from ride-hailing services. This is to fit a machine learning model to the whole route travel time. That, after all, is the goal, using features at the level of the entire route, things like the origin and destination location, the weather, the route length, the number of turns of particular kinds, etc. So you definitely can do this as a very natural approach. And people have compared the accuracy of these two different approaches, the segment-based approaches to the route-based approaches, and have different papers actually draw different conclusions about which one is more accurate, somewhat surprisingly. And so we actually did a theoretical analysis of this problem to try to resolve this question about what types of modeling approaches should be used in this context. And just to illustrate what is the dynamic that's going on, the segment-based approaches on the upside, they're sharing information for these overlapping historical routes, historical trips that drivers took. They're using all the data from a particular road segment to capture these detailed traffic patterns on that road segment, and they're using that information as they do prediction. So that sounds great. On the flip side, they do have an issue with accumulation of predicted error across the segments of the route because of that geographic granularity consideration that I mentioned. And so which of these dominates was an outstanding theoretical question. And so we did an analysis that actually shows that if we boil the problem down using some simplifying assumptions, then we compare the accuracy of these two prediction approaches, that the predictive accuracy of the segment-based approach is better than that of the route-based approach. Basically, that this ability to, the data sparsity issue that's being addressed by fitting at the road segment level dominates this other effect, which is the accumulation of predictive error across the road segments. And so this is a really helpful insight as we move forward in terms of developing these methods. So we do definitely need to incorporate these segment-based models for traffic as we do these predictions. There actually is no reason why we can't try to take the best of both worlds. And in fact, some some people have done just that. There's a nice paper in the literature that I'll mention in a moment. You can think about combining the advantages of this fully route-based machine learning approach with a segment-based machine learning approach. And in fact, there's a paper from DD Labs that does this by combining two types of route-based models with a particular type of segment-based model. And so for the route-based models, they have one approach that's more parsimonious, a more statistical model with fewer parameters, and then they have a deep neural network approach as the second approach. Again, these are both route-based models, and they're combining that with a segment-based model, which the approach that they use there is a recurrent neural network. So instead of simply adding up predictions across the separate road segments, like I mentioned before, you can actually have a recurrent neural network that tries to capture the sequential nature of this data using a recurrent structure in a neural network. And they do find some improved predictive accuracies by combining these two approaches, and they compare to some simply route-based machine learning models. And so here, if you look at something like using a gradient boosted decision tree at the level of the whole route in the first row, comparing to the combined approach that they're recommending in the last row, and you see that they're able to get 5 to 10% better than just using a route-based approach alone. So there are different ways of combining route-based approaches with segment-based approaches. This isn't only one, but it's one that's available publicly. And so this illustrates the dynamic, which is that this spatial granularity really matters. It's not so much the type of machine learning model that we pick, whether we pick deep neural networks or gradient boosted decision trees, although of course that does matter, but these issues of data sparsity and what is the signal you're actually trying to capture really matters. And so this decision about what is the granularity at which you're fitting the model and how do you handle those traffic effects at a very fine-grained level as you're doing prediction at this more coarse level is very important. And so just to summarize, these travel time predictions are used throughout ride-hailing apps. All of our pricing and dispatch systems, for example, it's one of these core technologies. And we showed theoretically that modeling the segment level travel times does considerably improve the predictive accuracy. And in fact, you can combine some of these segment-based approaches with route-based approaches to get the best of both worlds. Thanks very much. I'll leave some time for questions.
Hey, thank you, Don. This is terrific. We've got a question already from Stefan. Can you see the chat, or Stefan, would you like to go ahead and ask it?
Cannot. Oh, here we go.
Yeah,
I can just go ahead and ask questions. Okay. When I look at any kind of route planners and estimated travel times, I'm always happy if I can beat the estimated travel time, and I'm unhappy if I can't beat it, because it kind of gives me an endorphin boost that, look, I beat it by 5 minutes. So that kind of suggests to me an asymmetric loss function. So my question is, do you silently pad those estimates so you don't really give the expectation, but a like 60% quantile forecast or something?
It's a great question. The short answer is no. There are a couple of reasons for that. One is that, yes, conceptually, there absolutely might be an asymmetric loss function. Keep in mind that we have so many different customer-facing experiences where these travel time predictions are surfaced. They're also surfaced throughout our dispatch and pricing engines. And one of the principles that we've established is that we want to use consistent travel time predictions across all of those user surfaces. We want drivers to be seeing the same thing as riders. We want our dispatch system to be making the best decisions possible given the information that we have. And so because of that need for consistency across the surfaces, we actually decided that focusing on an unbiased prediction, for example, minimizes something like root mean squared error, or you could say maybe mean absolute error, or some standard kind of metrics is where we've gone. We also have a user principle that we don't want to mislead our users. And so we've made an explicit decision that we want to focus on trying to provide unbiased predictions throughout our experiences.
Okay, great. There's another question came in from Virginia.
Okay, looks like, how do you deal with having a more accurate model, which at the same time can calculate the predictions really quickly? Great question. So I would say that actually we don't always use the full featured model for predictions. So in cases where we have to have a large volume of predictions in a very short period of time, but where we're not quite as sensitive to the accuracy of those predictions, we can use a simpler model. And so we have a couple of different options there. And as I mentioned, thousands of calls to the ETA prediction engine for every trip. And so being a little bit careful about the computational resources that we use, for example, can be valuable. So then we don't necessarily do this full segment level prediction approach in every single instance. And in some cases, some of these approaches that I described where you just have a route-based prediction is the simplest thing and it's a reasonable accuracy, for example. So yes, depends on the sensitivity of the application to the accuracy.
If you're doing the forecast at the segment level, do you find a lot of correlation in the errors segment to segment, thus leading to the bias in the overall when you add them all up?
It's a great question. There absolutely is correlation of travel times across road segments, as you can imagine. There are underlying traffic effects that affect the whole road network that we may not actually have the features for explicitly. And this creates these correlations. There are correlations due to things like the fact that this is the same driver. And so some drivers drive faster than others, for example, which would affect the speeds across the entire trip. Keep in mind that if our goal is to predict and provide an unbiased prediction at the route level, our goal is to predict the expected value of travel time, that expected value sums across the road segments of the route because of the additive property of expectations. And that's the case regardless of the correlation. Now, the correlations, so if our only goal is to predict provide an unbiased prediction of travel time at the route level, we don't have to deal in a sophisticated way with the correlations across road segments, and we just focus on predicting the expected value of travel time on individual road segments accurately. The correlations matter much more when we start to think about providing an interval prediction for travel times, providing some uncertainty associated with that. And then these correlations really matter much more. And so yes, in those cases, you might want to include things like capturing the Markov structure. There is a Markov correlation. I should say that the correlation looks something like an overall effect at the route level that's due to things like the driver effects, et cetera, and some of these macro effects combined with some Markov dependence on top of that. And so actually it's a paper on my website that talks about how to handle that in order to get accurate interval predictions or probabilistic predictions of travel time if uncertainty is really important for your application.
Yeah, I think one more question that kind of came in anonymously, unless the person who asked it wants to reveal, but final question. How Uber's travel time predictions compare to those from, say, Google Maps?
How do our predictions compare to those from Google Maps? Let's see. I mean, I'm not going to answer that question directly, but what I will say is that our goal is not to fully reproduce all of the functionality of Google Maps in-house, for example. We have a much smaller mapping team than Google Maps does. We don't attempt to do everything around the world, all of these technologies, all of the map data, for example, in the same way that Google Maps does. And so we try to be much more targeted in terms of the technologies that we develop being the ones for which it's most important for us to capture Uber-specific effects. And those do occur in travel time prediction. There are specific effects because of certainly at the pickup stage, at the drop-off stage, there are some special things that happen in the ride-hailing context that are different from the type of data that Google Maps would have available as it's doing prediction. And certainly, as we're doing Uber Eats, for example, the driver behavior in Uber Eats is going to be different from the average driver using Google Maps. And so it is important, the travel time prediction problem, it is important for us to have predictions of travel time that can richly support Uber's use cases, and also because of the requirements, very strict requirements around latency for our systems and the extremely high volume of predictions that we need in order to support our app. As I mentioned, we do have to have in-house travel time prediction engine at Uber, but that kind of decision about, is this something that we want to invest in as an app, is very much focused on, can we provide a better user experience? Is there some requirement in terms of the latencies that requires that we develop it in-house as opposed to relying on a third-party service like Google Maps?
Right, fantastic. Hey, time's up, we're a little over, but anyway, fantastic, Don. We really appreciate you sharing your stuff with the ISF, and I hope we see you again soon. Thank you all.
Thank you so much, Mike.
Bye-bye.
Have a good one.